Alright, welcome back to Meteorology 101. In this video, we're going to talk about air temperature and continue our study series. So, air temperature. In the last video, we talked about heating of the Earth, the atmosphere, along with heat transfer mechanisms. So, how heat transfers, conduction, convection, radiation, and incoming solar radiation. So, if you haven't seen that video, go back and watch that one on heating of the Earth and atmosphere. So this video we're going to cover how air temperature varies daily, monthly, yearly, controls of temperature, organization of temperature data, and measuring air temperature with instruments. So the daily or diurnal temperature variations. Daily cycle of temperature is very much like the seasonal cycle. So warming begins in the morning. So that represents spring. Hot in the afternoon, representing summer. Cooling in the evening, representing fall. And coolest in late evening, early morning, represents winter. So you can see we get our hottest temperatures in the afternoon, coldest temperatures early in the morning, and see how they represent the different seasons of the year. So you can compare that to that seasonal cycle with a daily cycle of how the temperatures change throughout the day. So just like seasons, due to the differential between incoming solar and outgoing Earth radiation, so the incoming solar radiation from the sun and how much radiation the Earth is emitting, you get that differential change representing those seasons throughout the day. Daytime warming, as we covered earlier, was the solar radiation heats the Earth's surface, which in turn heats the air by conduction. So the air that's touching the Earth's surface, that is the conduction that heats that air from the bottom. So how this heat is distributed depends greatly on the wind. So if you have any mixing or not. So calm wind, hot air remains near the surface. So the heat that's being emitted from the Earth from conduction, the outgoing solar radiation touches the air, heats that air, and it just sits there because there's no wind or major pressure difference to create that wind to cause any mixing. Thermals are small, but don't bring much hot air up. So you will have little thermals as the surface heating happens. You can have thermals rise, but without that major pressure difference creating that wind to create low-level divergence and to give you that upward vertical motion to bring the hot air up. Temperatures 5 to 6 feet off the ground could be 30 degrees cooler. So just from your feet to your head, if you're 6 foot tall, can be a 30-degree difference. So that's why temperature measurements are not taken at the surface. So any air temperature weather station is going to be off the surface when that is taken. Also not taken in the shade or over grass because of that difference in radiation from the Earth over grass. That makes a big difference in the temperature also. So daytime warming. There's a thermal shelter. So if you look at the temperature, the temperature differences, like we said, 30 degrees difference between the surface and 6 feet. So that's why most weather stations actually have a thermo shelter that they store their thermometers in, wet bulb temperature, the wet bulb, so they can get those readings. Some stations still do that with a sling psychrometer and get a more accurate reading on the temperature, and that verifies the temperature sensor on the ASOS. All right, effect of the wind on temperature. On a windy day, temperature does not change much with height because you have the mixing. So now that temperature is mixed through the pretty much still lower levels, but up to 3 meters right here. So you get that mixing now that the temperature is more uniform, so you don't have much of a change of height on a windy day. The wind creates turbulent eddies, which transfers heat from near the surface upward and the cooler air from above downward. So you get that mixing, and temperature is pretty consistent throughout that layer. All right, maximum daily temperature. The sun is highest at noon So why does the maximum daily temperature occur around 4 p.m. or so? It has to do with absorption and emission. So how much incoming solar radiation you have from the sun, how much the Earth is absorbing, and how much the Earth is emitting out. So when do we have warming? When the absorption is greater than emission. When more heat is being absorbed than it is being emitted. This is usually the case up to about 4 p.m. average. So this is a thermal lag is the term for this thing. Incoming solar radiation, how much is actually being absorbed by the Earth, re-emitted from the Earth, and back up to create that temperature change through the day. So when your sun is highest at noon, it's already moved past before that heat is absorbed and then re-emitted to create that temperature in the air. So incoming solar radiation is greater than outgoing radiation until late afternoon, and warming continues until outgoing becomes greater than incoming. So if you look at the graph here, 6 a.m. sunrise, you start getting that incoming solar radiation as soon as the sun comes up. It's maxed out at noon, and then roughly 6 p.m., depending on the season, what season it is, sunset at 6 p.m. You can see the difference on the outgoing radiation from the Earth as it starts to absorb the sun as it comes up, and then starts emitting that. Its maximum is about 4 o'clock in the afternoon, and that's pretty much across the country. Also, maximum temperature, 4 p.m. is the average time when the maximum temperature occurs, but can be at other times due to several factors. What are they? Clouds. So clouds keep temperature lower and cause temperature max to occur earlier. So if you have a clear day in the morning, you can have the heating up that surface, a lot more incoming solar radiation, and then all of a sudden the clouds form, cover the sky, then you have the reflection back, so the incoming solar radiation is lowered, and your max temperature already occurred. Bodies of water. So air over water is generally cooler than air over land during the summer. Air can move ashore during the day and drop the temperature. Sea breezes are the good example. So like over Florida, if daytime heating creates low-level divergence on the surface, then the cold air from the ocean will rush in and replace that. So you get low-level divergence. A lot of times what you see in the summer is low-level divergence right down the middle of Florida. You get that daytime heating. The land heats and cools 3 to 5 times faster than water. So you get the daytime heating, land heats, creates that low-level divergence. You get a sea breeze from both the west coast and the east coast of Florida. Those will converge in the middle of Florida, create upper level divergence, and rush all that warm moist air up and actually create a line of thunderstorms down the central Florida. And large storms and their fronts during the winter, the passage of the warm fronts can cause high temperature and be late at night and or early in the morning. So if you have a large front, you can get an outflow boundary. From a large storm, you get the downdraft, the outflow boundary, bringing that cold air down to the surface, outflow boundary, and then cooling that surface and bringing your temperatures down. So, or the frontal systems during the winter, you get the frontal system passage. It's cold, and then in the middle of the afternoon, you get frontal passage. Now you have that cold air behind that cold front pushing in and then dropping the temperature significantly, creating your low pressure in the afternoon instead of in the morning. Now, factors influencing max temperature, the soil type. It all comes back to absorption and emission. Some types absorb more energy due to color, texture, and albedo. The soil moisture. The wet soil heats up slower, and some energy goes into the evaporation. So if you see the looks like steam coming off the ground, that will be the evaporation of that moisture as the sun comes up. If you have a warm soil, you can see the moisture coming off of that. Or sometimes even like blacktop, if it rains and then the sun comes out, it gets warm enough, causes that evaporation, and then you can see that steam coming from the ground. Vegetation, evaporation once again, as it holds that moisture, then the incoming solar radiation from the sun heats up the vegetation and creates that evaporation. Clouds, humidity, and haze, and they reflect radiation. So if you have clouds, humidity, haze in the atmosphere, real hazy day, the incoming solar radiation will be lowered because it reflects it back to space. Factors influencing maximum temperature. Ideally, to get the hottest daytime temperature, soil, which is a good absorber, sand for one, dry soil, no vegetation, no moisture in the air. And what kind of area does that describe? It's the desert areas. So comparing Atlanta versus Phoenix here, they're in the same latitude, same amount of solar radiation coming in, but Atlanta is humid, Phoenix is dry. Atlanta cloudy, Phoenix is clear, lots of trees, less trees in Phoenix, so you have a high temperature of 87 degrees in July on average, and in Phoenix you have an average temperature of 105. So just based on the surface and the environment, what kind of the differences you can see in max temperatures just based on incoming and outgoing solar radiation. All right, nighttime cooling. Around 4 p.m., the Earth starts losing more incoming radiation energy than it gains in solar energy. Both the air and the Earth cool by radiating IR energy, radiational cooling. And the Earth radiates at a greater rate, so it cools faster. So more incoming solar radiation from the sun, the Earth will absorb it, but when the sun goes down, the Earth will radiate much faster and get rid of that heat. Just as a near surface warms by conduction during the day, it cools by conduction at night. By late evening, early morning, air at the surface is cooler than the air above. All right, so nighttime cooling, radiational inversion, an increase in temperature with height due to radiational cooling at the surface of the Earth. So you get an inversion. So the troposphere where we live, the temperature decreases with height. So when you get this temperature cooling at the surface, then it will cool lower than the temperature aloft, so you have an increase in temperature and height. Now you have a stable environment. So now you have a capping inversion that will actually hold moisture, sound, sound vibrations, radio frequencies, stuff to the closer to the surface, just based off that inversion. So factors influencing minimum temperature: wind, light wind, colder temperatures. Strong wind is warmer temperatures. Wind causes cold air near the surface to mix with warmer air above, a less chance of an inversion. So your temperature, like I said, with more windy days, your temperature with height doesn't decrease as much because you have the mixing. So when you have the cooling at night, then you typically get an inversion in the morning, but as long as you don't have the winds to break that inversion, to mix that air and create, give you more of a steady temperature with height. You have to have an increase in temperature with height to have an inversion. And that's usually what happens, usually in the fall, those cool mornings, you'll get the temperature on the surface will cool, the upper levels will stay warmer, so you get the inversion, the moisture is trapped to the surface, and then you can get fog, radiation fog, stuff like that from that inversion. It'll cap all that moisture to the surface until typically about 10 a.m. when the temperature increases, the surface temp increases, or you get winds that will mix that air, bring that upper temperature down to the surface temperature, and breaks that inversion, and then that fog can dissipate. Length of night, longer nights, more time for radiational cooling. So like in the wintertime, you have your shorter days. You'll have colder temperatures at night in the morning because you have a longer night than you do day. Moisture in clouds absorb IR radiation and emit radiation back toward the Earth. That's warming. So your greenhouse effect, how much energy the Earth is emitting, and then as that heat hits the clouds will reflect it back to the surface, and it will actually keep it warmer. If the air is moist, we get dew, condensation, it releases that latent heat, and that's a warming process. Terrain, cold air is more dense, it's heavier than warm air, so it moves down slopes into valleys, called cold air drainage. Controls of temperature. These are the main factors that cause variation in temperature from one place to another. Latitude determines the amount of solar radiation at the surface. So as you are closer to the equator, obviously you got more incoming solar radiation. The sun is more directly overhead. And as you increase in latitude, then the sun is at an angle, so you get less incoming solar radiation. So it's colder near the poles. Elevation, as we know, temperature decreases with height in the troposphere. So the higher you go into the mountains, the colder it gets. And that's why you get snow caps on the mountains. Land and water distribution have different heating properties. So we talked about that was 3 to 5 times different in heating. The Earth heats and cools 3 to 5 times faster than water. So specific heat, the definition is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. That's the specific heat of an object. Water has a higher specific heat than land. It takes more energy to raise its temperature. So in summer, land gets hotter than water, and in winter, land gets colder than water. Ocean currents. So on the East Coast, the continent's warm currents flow to the north. West Coast continents, cold currents flow to the south. So coastal cities on the West Coast will likely have lower summertime temperatures because that cold current coming down, and then that cold water cooling the air, and will actually create a sea breeze from that. Cooling that air at the surface, it can push that air. That air gets heavier than the air over land, so it pushes in toward the land, creating a sea breeze. Okay, so large change in temperature from the tropics to the poles. Lines of equal temperature are called isotherms. Colder over land, warmer over water. So the main thing to get out of this is from the north and south temperature gradient is actually what causes the jet stream. So if you look at this chart, you can see the long wave trough over the United States. So this is January. So a polar outbreak, the cold air over Canada pushes south, and now your temperature gradient, north-south temperature gradient from the equator to the poles has shifted south. So now you have a long wave trough with the jet stream. So the north-south temperature gradient is the cause of the jet stream. Less change in temperature from the tropics to the poles, a small temperature gradient, that's in July. So you have your semi-permanent high pressure systems, and the semi-permanent high over the Atlantic will actually push north in the summer. So you have less of a temperature gradient from the land to the water, from the north to the south. So your jet stream stays pretty uniform. You'll still get those long wave troughs, but they won't drop down further into the southern United States like they do in the winter. So organization of temperature data. We arrange the air temperature data two main ways. By averages, you'll hear that a lot, how what the average temperature is for this time of year. And then by ranges, what's the min-max temperature ranges between what's the range between the minimum temperature and the maximum temperature throughout the day. So if we look at a low of 70 and a high of 90 on a particular day, then the average or mean temperature is 80 degrees. The daily range is 20 degrees. So which one of these tells you more about the temperature of any given area? The organization, let's see, the daily mean temp. So in a desert town, 80 degrees. A coastal town, 80 degrees. You have a low of 55. But in a coastal town, a low of 70. High temperature in a desert town, 105. In a coastal town of 90. So same mean daily temperature, but very different weather. So your ranges are always going to be more spread in a desert town because radiational cooling at night in the desert. There's the dry sand. There's really nothing to absorb that energy. It releases it, takes in more heat during the day, releases it faster at night, and you'll have a much wider range over in a desert town than you will a coastal town. At any location, the difference in temperatures between the coldest and warmest months is called the annual range of temperature. And the largest annual range of temperature occurs over land. Because like I said, water takes a lot more energy to heat and cool water, to basically heat the water up. So you'll have a lot less of a change in the water temperature. In areas with large annual changes in solar radiation, near the Arctic Circle, 112 degrees Fahrenheit. And smallest annual range of temperature is over water in the tropics and islands near the equator, 1 to 2 degrees Fahrenheit from warmest to coldest. So the average mean annual temperature doesn't tell us much without the annual range of temperature. So Richmond and San Francisco have the same mean annual temperature, but their climates are very different. Water moderates temperatures in San Francisco. So we talked about that over West Coast. You got the cold currents that come from the north, and that will moderate that temperature over San Francisco much differently than the warm currents over on the East Coast near Richmond. Alright, so wind chill factor, how cold we feel due to temperature and wind. That's the definition of a wind chill factor, so a lot of arguments on that one. Why do we feel colder when the wind blows? Because the heat from our skin actually conducts the air, warms the air around it by conduction, and then the wind blows that heat away, and then our body has to produce more heat to continue to warm that layer to make it feel like a warm blanket around us. So as long as the wind is blowing, your body can't produce enough heat fast enough to keep that layer of air around your skin warm, so you feel colder. Fast wind, faster loss of body heat. And what about cold and moisture? We feel colder when it's also wet outside, because like I said, it takes a lot more energy to heat the water, so water conducts heat better than air and can cause hypothermia, big problem for ill-prepared hikers in the mountains. So it's like when you're sweating, you're actually cooling down. So in the wintertime, you are sweating, but your sweat evaporates so much faster, and that creates cooling and you really sometimes you don't even realize your body temperature dropping, or you're starting to become dehydrated because you're not actually sweating that water out. It's evaporating as you're sweating. All right, so the measuring air temperature, we use thermometers. How do they work? They don't measure air temperature directly, but rather the effective air temperature on different substances. So water, mercury, alcohol, and metal. That's just a few things that we use to measure temperature. The most common are called liquid in glass thermometers. The liquid is usually alcohol, if it's red, or mercury. So the maximum thermometer uses mercury. It has a restrictor, a constricted area. As the temperature rises, it pushes through that constriction, and then it will not just drop back down to the bulb and lower the temperature right away. So these were used like in doctor offices years ago. You'd see them shaking the thermometer. They would shake that mercury back to the bottom of the thermometer, and then they would check your temperature, and when they pulled it out, it wouldn't start dropping immediately, so they could get a good read on that temperature. Minimum temperature uses alcohol. It has a lower freezing point than mercury. Most important feature is the index. It can be forced down the bore, but not back up. So when the index marker pushes down, that goes to the minimum temperature, and then if that thermometer is moved into another environment, it will not move right away. So they can get you can see the minimum temperature for the day. So even if the temperature changes, the thermometer doesn't. Bimetallic thermometer. The temperature is measured by the expansion of brass. This is used in most thermostats. So thermostat in your house. The old thermostat, you could pull the cover off and you see the winding, and as that brass expanded or contracted, then the temperature would change. So you'd see the thermometer. It was an analog needle that would move and show you the temperature in your house. Same thing was used on that thermostat. When that expanded, it would actually move that coil and then expand to a point where it made contact and connect two wires together and actually turn your air conditioning on. Same thing with the heat. It would contract and then drop down and then turn the heat on. So that's pretty much going to end this video. We'll say again, thanks for watching. Visit my website, meteorology101.com. A lot of information over there. And until next time, get your head in the clouds.